네, 여러분 안녕하세요. 네. 자, 여러분 안녕하세요. 혹시 질문 있으시면 질문을 해주시고요. 지난번에 우리가 이제 AC 시뮬레이션을 하는데 그걸 풀로 트랜지언트 시뮬레이션을 하지 않고 퍼터베이션에 대해 가지고 만들어진 그 스몰 시그널 방정식을 직접 풀어서 해보자 라고 이렇게 말씀을 드렸었죠. 그것을 풀다가 있었던 어려움 같은 것들에 대한 질문을 받도록 하겠습니다. 먼저 그것이 끝나고 나면 본 강의를 시작을 하도록 할게요. 따로 뭐 어려운 게 없었다 그러면 그냥 답변 남겨주시고요. 네, 박건우 씨, 좋은 지적이십니다. 네. 또 다른 분들도 다 이렇게 일단 다 받고 그리고 나가지고 박건우 씨의 질문에 대해서 답변을 해드릴게요. 네, 한성미 씨, 알겠습니다. 네. 자, 그러면은 세 분 모두 그 숙제를 하는데 어려움은 없었나요? 그러니까 결과는 나왔고 그 다음에 그 결과가 여러분들이 예상한 것과 비슷하게 나오고 있습니까? 네. 어디 그래요? 자, 이게 17번이었죠? 네. 자, 그러면 박건우 씨와 그 다음에 한성민 씨의 질문에 대한 답을 해보도록 할게요. 첫 번째로, 왜 여기서는 그 전에 베르누이, 네, 알겠습니다. 자, 정성목 씨 알겠고요. 박건우 씨 질문에, 그리고 한성민 씨도 같이 질문하신 이 베르누이를 사용하지 않은 이유에 대한 답은, 지금 제가 여러분한테 시킨 게 실제로 쓰이는 방법이 아니기 때문에 그렇습니다. 그렇기 때문에 어떻게 하든 별로 상관없다는 그런 마음으로 그냥 뭐 말씀을 드린 거고요. 당연히 베르누이 함수를 사용을 하지 않은, 그러니까 샤페터 분매 스킴을 쓰지 않은 방법으로 이산화를 했기 때문에 에러가 있겠죠. 근데 그 에러는 실제로는 있어서는 안 될 에러고요. 그런데 그건 지금 우리 하고 있는 방법의 자체에서부터 나온 거기 때문에 별로 중요하지 않다. 그래서 그냥 계산을 해보라고 이렇게 얘기를 한 겁니다. 그리고 네, 두 번째 질문도 생각을 해보면 AC에서 델타항에 대한 고를. 네, 그러니까 오늘 하려고 하는 일이 그래서 진짜 사람들이 하고 있는 AC에 대해 가지고 설명을 하려고 하는 것입니다. 그러니까 오늘 수업을 들으시면 질문에 대한 답변이 될 것이라고 생각이 되네요. 자, 그러면 또 다른 질문 있으신가요? 질문이 있으시면 또 질문을 받고 없으면 시작을 하도록 하겠습니다. Okay, so if you don't have any further question on lecture 17 or homework 17, then I will move to lecture 18. So this is the second part of our discussion about AC simulations. So AC simulation for our device simulation. So if you remember correctly, so what we have done up to now is like this. So eventually we have to solve three equations. You know what they are. So Poisson equation and electron continuity and hole continuity equations. We have to solve this set of equations in general. So if we consider arbitrary shape of input signal, for example, let's say that this is input bias voltage, and if we assume, for example, such kind of pulse, periodic pulse applied to the system, then actually we have to solve a coupled set of three equations. That is the usual case. However, instead of this general waveform of our input voltage excitation, now in this AC field, so we just set a DC bias voltage and say that we are now considering this type of voltage excitation. So now in this case we say that okay, since input is decomposed into V in its DC component and yes, V in its AC component. Yes, both of these two components will generate a certain reaction, so certain response of our system. So what we expect is, okay, since we have this DC excitation, so we will have, for example, out DC. Of course, here, although I have like I out, the output current, but you know, in order to calculate output current, we have to evaluate all the physical quantities inside our system. So please treat our I out as a representative quantity for system's response. So we have this output response, and also we will have this output response, which is linearly dependent on the size or magnitude strength of the perturbation, first order perturbation. So we assume that So from the viewpoint of their magnitude, this is treated as large, and this y is treated as small. So the relation from this to this, that is rigorously treated by solving this set of equation. And since the first order component like delta V in or delta I out are small, so we will assume that their motion or their relation can be expressed by a set of equation which is obtained from just a small signal analysis. I mean that since the signals are small, if the how can I say, so delta V in, this is small, and delta I out, and this is small. So this is first order and this is first order. So in between we have to have just a linear relationship. Otherwise, if we introduce, for example, a quadratic term in it, then eventually this quadratic term will generate, for example, second order of delta V in. However, this is not allowed in our treatment because we are assuming that delta V in is already quite small, so their multiple product is not is really negligible in its magnitude. So today, not today, but in the previous lecture on Tuesday, we have thought about what is the relationship between this quantity, so voltage excitation, and its small signal response. And what was the result? The result was, once we have a set of equations shown here, then we can introduce small signal Poisson equation, small signal electron continuity equation, and small signal Hall continuity equation. We can build those equations, and by solving those equations together, you will get the propagation or evolution of your quantities like delta V in, of course that is given, but delta I out. That was the summary of our previous lecture. So do you have any question? So in order to derive these AC equations, we have made such kind of an assumption. Any kind of a quantity, let's say that, for example, phi, then this is decomposed into DC and yes, it's a AC component. And after that, we just evaluate Poisson equation, for example, and also we evaluate DC Poisson equation without this delta term. So make a subtraction, then we will get certain expression which contains delta phi in it. However, in general, it can generate non-linear terms. However, just to neglect non-linear terms, then you will get a linearized AC Poisson equation. Of course, in the case of Poisson equation itself is a linear equation, so you don't have to worry about that. But if you consider, for example, electron continuity equation or Hall continuity equation, they are really nonlinear equations because there we have the drift term, which is a product between electron density or hole density and electric field. So they are really non-linear. In that case, we have to implement or introduce the linearization. Although the difference between the exact electron continuity equation and DC electron continuity equation, usually we will have some terms like delta n and delta phi. However, this term is neglected, just neglected, because we have assumed that this is quite small enough. Okay. So then now I will assume that in this today's lecture, you know the exact form of your AC Poisson equation and AC electron continuity and AC hole continuity. So if you have done your homework 17 properly, then it's not that difficult to understand my explanation. So if you have any question, then please let me know. But you know, our main lecture, L18, lecture 18, start from exactly from your question, like Mr. Park and Mr. Han asked me why the discretization of these AC equations, like the AC Poisson, especially AC continuity equations, are different from the discretization of electron continuity equation and hole continuity equation. There can be a certain deviation, so that's true. So do you like it or you don't like it? So in this case, we have to make a consistency between our DC discretization and AC AC discretization. So that is my point. So let's think about the electron continuity equation, because Poisson equation itself is quite easy. So and that is really linear. So we don't have to worry about the Poisson equation. So we can concentrate on the electron continuity equation. Of course, hole can be treated in the same way. So yes, let's write down like minus 1 over q, and we have to have this form. So I will explicitly write down in this current density, you know it, q mu n phi plus q dn gradient n equal to 0. So 1 over q is just gone, and gone. So we will have this form. Yes. And now you can easily do the linearization. So instead of this n, the total electron density, now you can write down the equation for your delta n and delta phi. Yes, you can do it. So let's do it together. Round over t and delta n minus, yes, divergence of, here we have a nonlinear term, so we have to consider this one, delta n and dc. And another one is mu n and dc, yes, delta phi. And finally, we can have dn gradient of delta n equal to 0. So you know it quite well. This is, once again, this is the AC electron continuity equation, and this is just electron continuity equation. Yes, they are the same, and as I remember correctly, you have tried to solve this equation. Yes, so you have it. But point is, here you are working on this two linearized term, and maybe it's not that comfortable to treat this term individually. For example, instead of this, this term, yes, instead of treating two terms individually, so usually what we do is introduce a certain type of discretization, so-called Shapiro-Gumes scheme, to make it more robust from the numerical standpoint. Okay, so we know that this is there is a little inconsistency. So, so one strategy is just to neglect that inconsistency. Okay, we can live with it. So don't worry about that. Yes, however, now I wanted to point out we have a better way to do that. So if you have any question, then please let me know. Now, what I want you to say is, please think about the Jacobian of your DC, DC simulation. Please think about the Jacobian of your DC simulation. So in this case, of course, the equation you have to solve is just given by, yes, this one, un n plus dn, yes, and we are talking about this term. When you talk about the Jacobian of your DC simulation, what you do is usually calculate something like this. If you say this is a certain function of n and phi, what you do is just to take the partial derivative of f with respect to n and partial derivative of f with respect to phi. So solution variables. So change of your f with respect to small deviation of your n and phi. So now let's think about it. So now I'm saying that what you do is just to calculate lambda f over lambda n. Your Jacobian matrix contains a component corresponding to lambda f over lambda n, and also it contains lambda f over lambda phi, and this is an element of your Jacobian and Jacobian matrix. However, the equation itself is not Jacobian. The equation is represented as a product between your Jacobian matrix and your update vector. So you know it. So what you do is, actually when you calculate lambda f over lambda n, it is assuming that now you have update for your delta n and update for your potential, so delta phi, and taking some of these components. So are you with me? It means that, simply speaking, this product between Jacobian and update vector can be considered like this. So f, which is evaluated with ndc plus delta n, and phi dc plus delta phi. First evaluate it and take this ndc phi dc. So if we have to evaluate this one, once again I will just repeat this first line. So if we have to make this change, then I will like to in this way, taking round f round n, taking the partial derivative and delta n. Also taking the partial derivative with respect to phi and delta phi. That will be the form of our two difference between two terms, like f evaluated with perturbation terms or updated terms, and minus n calculated with only DC solution. So simply speaking, your product between Jacobian and update already have the thing like this. You have it. Then let's come back to our AC analysis. In AC analysis, what you do is just to evaluate your Jn with ndc and delta n, phi dc plus delta phi, and make a difference ndc phi dc. So now you can understand this procedure required for the AC electron continuity equation is exactly same with that is already used in your Jacobian matrix. So simply speaking, although we have an electron continuity equation here, but point is part of this AC small signal electron continuity equation can be immediately obtained from, yes, this can be obtained from DC Jacobian matrix. So of course this is not exactly DC Jacobian matrix itself, but it is the product between Jacobian matrix and your update vector. But anyway, you can find this information just directly from your Jacobian matrix. Okay, so could you please, all of you guys, please confirm that you have understood the situation or my explanation. So simply speaking, AC electron continuity equation or small signal electron continuity equation, part of it can be directly borrowed from our DC Jacobian matrix. That's it. So everybody, please. Okay. Oh, good. Actually, Mr. Brock, your question is, or your understanding is correct. So, in order to implement AC equation, actually we have two terms. One term is corresponding to the time derivative. So, the time derivative term is shown here. Yes. So this one should be treated separately. But we have another term which does not depend on the time derivative. So this term, this perturbation which is instantaneously dependent on the solution variable, that can be immediately found in our DC Jacobian matrix. Okay, so Mr. Han, okay, so I will explain it once again. So in my opinion, actually, all of these complicated notation makes you very uncomfortable about understanding all of this guy. So let me just consider really simple equation. So instead of full this DC case, let's think about much easier case. So how about this? Okay, good. So this concept is important, and this concept is not that easy. So just let me repeat again. However, with much simpler equation. So let's think about this guy. Yes, now you have V in of T, and now you have, yes, R, and here you have capacitor, and you will take this node voltage as an output voltage. So now you know that this is just RC circuit. So let me just try to solve it. First of all, we have to apply the KCL for this output node, you know. So in general equation, we have to write down this way. So flux or incoming current through this R, and outgoing current through this C should be the same. So V in minus V out divided by R. That will, yes, that will generate us the resistor current, and that should be matched with what? So capacitor current. So we have to have C dV out and dt. Yes. So this is general equation. So when we just make a simplification, let's just manipulate it. So RC, now you have it. And yes, so instead of this RC, this is just a time constant, and yes, let's call it as T. Then we will have this simplified form like dV out over dt plus V out divided by the time constant tau is matched to our excitation like V in. So that will be the equation of our interest. For a while, just forget about the complicated drift diffusion model. Just concentrate on this guy. Okay, of course, all of them are time dependent variable. Okay, so up to now, so are you all with me? All of you three guys. So are you with me? Okay, great. Then now think about this one. We have to solve this one. So in general, what you do is, in general transient simulation, what you do is, okay, now I will make a discretization for our time derivative. So V out and time instance of I, and their difference from its previous time I minus 1, and Ti minus Ti minus 1 can be the simplest expression for the time derivative dv over dt, and here we have v out and time t divided by time tau can be written as this form. Yes, so what you have done with your complicated diffusion model is actually in principle identical with this approach. Of course, you have much more complicated terms in your implementation, but please note that this is just a complication of instantaneous part. When you consider this time transient part, you are the same in that standpoint. So now this is a transient case. Now we consider, instead of this transient case, we now go to small signal. Then now we assume that V in, that can be decomposed into V in DC and delta V in, also V out can be decomposed into V out DC plus its perturbation. So now you can first think about the DC equation. The DC equation simply says that the first time derivative is gone and V out DC divided by tau equal to V in DC and tau. So are you with me? This is a DC equation. Why do we have this the equality between DC input and DC output? Because at low frequency, the zero frequency, so now this one does not conduct at all. So this capacitive branch can be regarded as just a disconnected line. So there is no connection of our V out node to the ground. So they are just connected. They means that V in node and V out node. Okay, so this is DC one. And this is DC. And if we consider the general one shown here, now we can write down the total one. So now we have delta V out over dt, because yes, this one don't have it, and V out dc tau plus delta V out tau equal to V in dc divided by tau and delta V in divided by tau. This is the equation containing this term and delta terms. And please make the difference between them so we can easily understand. This term is cancelled out and this term is cancelled out. So we will have just a simple form, really simple form of this one. Yes. This will be the small signal equation we will try to discretize. You know, this is the situation of our previous lecture. We have spent our one single lecture hour to understand this is the form for Poisson equation and continuity equation. So I just repeat the same procedure for this simple RC circuit equation. So I hope that everybody now understand. But point is, let's say that let's assume that this is too difficult to you. Oh, of course you can say that, oh, this is not that difficult to me. I can easily implement it. So, okay, you're right. That is quite easy, but think about that you have some difficulties to implement it and you wanted to take it from your DC case. So let me just revisit your DC simulation. Oh, but DC simulation in this case is so simple, so I don't have to do anything. So maybe you say so, but it's not. So think about this one. From our discussion, you have to solve the this one, dc tau equal to v in dc tau. Think about your calculation. So you have a temporal v out. So you have the temporal v out after your case Newton iteration index. Okay, now this is your Newton iteration. Then let's say that you're even after the case Newton iteration, when you evaluate this residue, you find that, oh, it's not zero. So what you do is just to take the portable form of this one. So what you do is, now think about this one. Exact solution can be written as this temporal solution, which is not perfect, and delta V out, yes. So DC, for example. Then by inserting it into this form, yes, not exactly this form, so this seemingly exact solution to your original equation, what you can calculate is now tau dv out dc, the temporal solution, minus update vector minus tau v in DC equal to 0. So although this was not 0, so unfortunately, now we assert that this is really 0 because we have a good, really good update vector for our correction vector for our solution variable. So what you do is like this. Now we have here minus delta V out DC tau equal to, yes, so minus V out K DC tau plus V in DC tau. Okay, so I made a mistake here. Why do I have a negative sign here? Oh, sorry about that. Here we have a positive sign. Yes, so here we have a positive sign. So now you have the equation for your update vector, and please think about this update vector. What is it? This is just minus of your residue. And how did you calculate this guy? This guy can be decomposed into 1 over tau multiplied by delta V out DC. You know, later this guy will be treated as a update vector, and this guy will be the Jacobian matrix. So if we consider multiple of equations, then we will have this generalization step. So you know that, please come back here. Here we need the terms like delta V out divided by tau. Of course, here delta out is corresponding to AC response. And you know that in this case, this is not the drain, this is not the AC response, but it is just correction or update for our DC simulation. But point is, they share the same coefficient. 1 over tau is shown here. And just changing the interpretation of your delta. Previously you saw it as just this component, but when you say this is no longer this component, but the time perturbed quantity, then you can immediately reuse your previous Jacobian matrix. So that is the thing you have to understand. So equivalence between this term and that term. Why do we have the equivalence? It is only because the small signal analysis is not much different from the Newton iteration. So in Newton iteration, you always perform the linearization of your system with respect to the small update vector. And in the case of small signal analysis, you just make another linearization under the assumption of a small voltage excitation at the terminal boundary. So now you understand the equation, the governing equation, the Drifted diffusion equation. It is the same for all cases, and we now try to remake a linearization of that equation. So since the mother equation, the starting equation is the same, and the technique linearization is also the same, so that's the reason why, although they are built in a different context, but their functional form, their value are the same. Okay, so up to now I have just explained the procedure of AC and AC simulation and DC simulation, and make a comparison between our Newton iteration and the AC analysis. So in both cases, we are heavily relying on the linearization step. And since the linearization is used, so they have the same coefficient. So you can reuse it for this time instantaneous term. So it simply means that, oh, now you can, yes, you can reuse this term. However, this term should be treated individually, separately. So I will explain it after you are all clear about this concept. So now I wanted to ask our students to confirm that you have all understood this concept. So since linearization is shared for both cases, Newton iteration, DC Newton iteration, and AC analysis, the Newton iteration, the Jacobian matrix used in the Newton iteration can be reused for the AC analysis. Okay. Could you please confirm? Or if you have further question, then please let me know. Then I can explain again and again. Okay. Okay. So, Mr. Han, so good. Um, so okay. Okay. So now this is the third time to make an explanation. So let me just go to more formal explanation. So now you more or less understand what is going on, but you need more exposure to the equations. So let's do it together with me. So simply speaking, let's assume things like this. Now you usually what you do is like this. Now you have a certain quantity like Q. So what is the Q? It really depends on the situation. And let's say that you have, yes, I. Of course, you have certain things like C, but for a while, just okay, so for a while, just to forget about it. So just to make it in this way. Let's say that this is the equation you have to solve. So now think about one DC simulation. In DC simulation, of course, it has your solution variable, and let's call it as what? So what will be the appropriate name for your solution variable? Let's say that just S. This is a solution variable S, and yes, this is S. If we adopt this expression, then our goal is, for this case, our goal is to find out a solution which is satisfy this form. Because this time derivative term is gone. And if we consider AC case, AC simulation case, then now we will say, yes, now we have to delta Q delta T, and yes, we have delta F equal to 0. What is delta F? Yes, delta F and delta Q can be written as like this. Delta Q is given by Q, which is generated by S dc plus delta S minus Q S dc. Of course, delta F can be defined in a similar way. The calculate the value with the perturbation and take the difference from the function evaluate with only DC solution. So now this is the situation we will have. So our goal is the similarity between this delta F implementation and DC calculation. Think about this one once again. Now we are at the case Newton iteration. So we have SK. Yes. This is our temporal solution, and we wanted to have the condition like this. F of SK equal to 0. This is our hope and this is our desire. However, unfortunately, since SK is not the correct solution, so yes, unfortunately we have a non-zero value. Oh, we want to have a null value for this one, but it doesn't. Then how about this? In the k plus 1s, the next Newton iteration, we wanted to have a sk plus 1, and that is just given as sk plus delta s. Of course, here delta s should be regarded as an update for s. So by adding delta s to s sub super k, then we will have the real solution. We hope that this is the last step of the Newton iteration. So we wanted to have real solution. So just insert it to our DC equation once again. Although sk was not the solution, but the sum of sk plus delta s Yes, that is equal to 0. So it means that it just represents our hope, our desire. Okay, although sk is not perfect, but when we just add delta s, it becomes perfect. So in this case, we do such an expansion. So with f sk and plus round f over round s and delta s equal to 0. So from this one we will have simple equation like this: s equal to minus f of sk. When you have your system, usually what you say is this is the residue vector, this is the update vector, and this is the Jacobian matrix. So now you have this form. But if we follow exactly same manner, so let's visit our delta f once again. Then we have the terms like this. Where is it? F evaluated with SDC plus delta S. So you know this is quite similar with this one, and we have applied the expansion technique. So now we will follow the same procedure, evaluated at SDC plus round f over round s delta s minus f s dc. You know, fortunately, we have cancelled out here two terms, and we have just round f over round s delta s. So now we can find out once again round f and round s. And what was it? So in the DC case, we called it as the Jacobian matrix, and same thing can be found in this one. So now previously in this one should be regarded as update for Newton iteration, and this one should be AC response of solution variables. So their physical meaning are different. However, once again, we can clearly find that this and that are shared. So what you can do is, usually in order to perform your AC simulation, first of all you have to perform your DC simulation. Now you have a Jacobian matrix, and that Jacobian matrix can be used, or the routine for generating the DC Jacobian matrix can be reused without any modification for this delta F term. Of course, we have not thought about this delta Q term, but later we will talk about it. And for this case, this is exactly same as before. Before means the DC Newton iteration. So, okay. So in today's lecture, I have tried three different explanation. One was directly related with the electron continuity equation, and second time I used RC circuit, and the third time I have used a more generalized form, but without any difficult notation. I wanted to emphasize on the similarity between DC and AC simulation. Okay, so are you guys with me? So Mr. Han, especially, could you please give me whether you have understood this all of this discussion? Okay, so then now you have homework number 18. Instead of that, now you have homework number 18. Now, instead of solving your, how can I say, uh, homemade scheme for discretizing this AC electron continuity and hole continuity, please just reuse your DC Jacobian matrix. So that is one thing. And I have another thing. Here we have round over round t. This is true for our time domain signal. However, in reality, we make frequency domain expression. Then simply, in the case of time domain, instead of in the case of frequency domain expression, this time domain signal, or this time derivative operator can be just written as multiplying an additional factor j omega. So I think that's it. So please now implement your full AC routine. I mean that in this AC routine, you should not perform real transient simulation. No. Homework number 17. You made the transient simulation for the AC part of the equation. Please don't do that. Just use one-shot simulation. So how can you do that? So please reuse the DC Jacobian and just add the term like j omega delta q. More exactly, if we are considering something like a round delta n over round t, then please convert it into j omega delta n. Yes, then your now your AC matrix will contain this imaginary part. So your question is, can we make a matrix inversion or matrix vector solver for this complex matrix? Yes, of course, you have the capability, whatever you insert. So your matrix solver can solve the complex matrix. So just add this j omega delta n terms into your DC Jacobian, and that will give you the immediate solution about your AC response. So now, instead of having the tedious transient simulation in order to get the eventual solution, just directly solve only one single equation to get the same equivalent solution. Okay, so are you with me? I will just have time to listen your question. about homework number 18. So otherwise I will wrap up today's lecture 18. So I think that this is the end of small signal analysis, and now we will move to another topic. Okay, good. So other two students, Mr. Zhang and Mr. Park, please confirm that you have no further question, or if you have question. Okay, so okay, Mr. Park, then yes, so in your transient Jacobian matrix, previously you treat your round n and round t term with ni plus I minus ni minus 1. Here, of course, I is representing the quantity of Ti. But instead of that, this is the time transient one. But now, just to introduce this one, then you will have a very similar Jacobian matrix, but this is modified for your AC simulation. And by solving this AC Jacobian multiplied by AC response equal to your voltage perturbation, you will get the immediate solution for your AC simulation. So simply speaking, AC simulation is really cheap, much cheaper than full transient simulation. How can we have such a magical result? Is it only because AC simulation is just concentrated on the small perturbation. So transient simulation can do anything. So it can solve many different not so small perturbation, but AC analysis is restricted to the small signal perturbation. So once we restrict the applicability of our analysis, then we can achieve numerical efficiency. So what we have sacrificed is the generality. So AC simulation cannot be applied to more general cases, but instead of that, our AC response calculation becomes much faster. So that is really useful for our real calculation. For example, if we are talking about the RF device, like you are working in a company to provide RF CMOS, then what will be the cutoff frequency of your device, or maximum oscillation frequency of your device? Of course, you have to be able to calculate those quantities, and AC simulation can provide you such valuable quantities almost immediately. So compared with even this simulation, this H simulation is much cheaper. So this simulation, we need multiple Newton iterations, but you know, this AC simulation is obtained from just one Jacobian inversion. Of course, we don't actually make a Jacobian inversion, but anyway, this one matrix vector equation solution. So AC is much cheaper than DC simulation, and yes, so we love it, and we are frequently using this simulation technique. For example, if you are working in the DRAM company, then in the case of a DRAM company, they are critically interested with the capacitive component. You know, DRAM has capacitor in its own, so separated external capacitor connected to the DRAM transistor. However, even in our DRAM transistor itself, we have many capacitive components, and accurate calculation of those capacitive components that is critically important for calculating the real refresh time for our DRAM product. So DC, not only DC, but such kind of AC analysis is really widely used in industry. Okay, so since time is up, if you have a further question on homework number 18, then please leave a message through our Slack channel. Okay, thank you. Bye.